Here's some test cells I've been working on for being able to quickly test out the cation exchange membranes and then anion exchange membranes as well, but I haven't gotten around to trying and making any of those yet. So the idea, here's couple of the first iterations, is you have an O-ring here in the middle. It's kind of hard to see. An O-ring groove, and then a Viton O-ring sits inside, and you have basically two sides of the cell, and they clamp around the membrane like so, and the O-rings form a seal. That was kind of the design idea. Quickly ran into the first problem of these 3D printed cells have ridges from the layer lines, because I just used FDM. It's like fused deposit material or something like that. Forget what it stands for, but anyway, an FDM printer, and so it prints in layers, and you can kind of see the layer lines. And because of that, it makes it kind of hard for the O-ring. The Viton O-rings are somewhat stiff, and so it's hard for them to seal against these layers. There's slight leaks, and so that's one issue with this, but I got around that by using this vacuum silicone grease. I think you can pretty much use whatever silicone grease. I just have this on hand because of some other stuff that I work with, and that works really well because the silicone is pretty hydrophobic and it forms a good seal. And so I've had this guy sitting, and if I can zoom in a little bit here, so you can see where the two O-rings kind of meet together in there, and there's no water or anything leaking through. There we go. You can kind of see where the O-rings meet. So this seems to be working quite well. The other kind of consideration is how the O-ring is going to seal against the membrane itself, and so I'll be testing that for a few hours. Now that this is holding well, I'm going to move on to actually testing for any leaks with a membrane sitting in there. Here's the cell taken apart. You can see the Viton O-rings, and it just comes together like this, seals against whatever membrane you put in there, at least in theory. So I just made a new membrane not too long ago to try and improve on the last one that I made, because the last one, these are actually somewhat tricky to get right, because you really want to get all of the fiberglass coated and not leave any open fiberglass. And the last membrane I made definitely didn't have full coverage, whereas this one should be a bit better. It's still not perfect. I think this is going to require some more iteration, but this one should be much better than the previous one. So I'm just going to cut a small piece of it. Create a kind of fast test, a quick and reliable test bed for these membranes, because I really didn't like you know, doing the sort of the hot glue method, it felt a little janky, and I didn't feel like I was very good at it either. So figured I would design something like this that would help me out with testing these things more quickly. Okay, so now we have our membrane. So we're gonna place it about like so. Then we put the other cell on top. Line up the bolts. And before committing to tightening everything down, just want to double check that the membrane is actually in between the O-rings all the way around. I don't know how easy that is to see, but it is between the O-rings. I think another design improvement I could make on this thing is to bring in the distance here from the wall to the hole, so that way the nut sits against the wall, and you can I don't have to hold the nut. Basically I can just turn the bolt and it will pull the nut in and make it a little easier to put these things together. But overall, so far this is quite promising. So now I'm gonna fill this with water, and I'm gonna let it sit for a few hours and see if we get any leakage, and we'll go from there. The two things we're looking for is obviously we don't want leakage coming from inside the cell to outside the cell and just leaking water or solution out. And then the other thing is we don't want leakage through the membrane itself from one side of the cell to the other. We're making the assumption that that isn't going to happen because the membrane is impermeable to water with the current recipe. So I'm just going to fill both sides up with water, and then we will kind of track it. All right, here's the cell with the water. We'll just leave it in there for a while, and hopefully there's no leaks around the membrane. Alright, I've let it sit with a membrane installed in between the cells. I also labeled the material that the cells are printed out of, because one of the advantages to doing this with a 3D printer, or I guess one of the workarounds, it's not necessarily an advantage, is some materials are really good with high pH levels, some materials are really good with low pH levels as a generality, but most, at least 3D printing materials, don't handle both well, unlike something like Teflon where it'll pretty much handle whatever, or PVC like Rowow uses. So for the tests, especially if you're running some long-term experiments, you could take advantage of the fact that because your membrane is making one side acidic and one side basic, you basically print the you print the two cells from different materials that will accommodate each pH level. But yeah, so I've had this sit for a couple of hours now, actually more like 4 or 5 hours. There's no leakage whatsoever between the cells. So basically the seal between the O-ring and the cell is good. The seal between the O-ring and the membrane is good. So there's no water whatsoever leaking outside. And now I think what I'm going to do overnight, just to see before I start actually do a couple of proof of concept experiments with the membrane in between before I actually do some electrolysis. I'm gonna fill up one side only with water, leave the other one empty, leave it overnight, and make sure I don't have any water penetrating between the membrane. Alright, I've filled up one side, left the other side empty. Maybe I can take a look at it from the top just to show. There's the cell. One side is empty. Let's see the water in there. And there's the other side of the membrane in the cell. Totally dry for now. We'll check back tomorrow morning, see how it holds up. And if it's good, then tomorrow I'll actually do some electrolysis in this and show that. I let this thing sit overnight, and there's no sign of leakage from the filled cell to the empty cell. No sign of leakage between the cells. So I think this thing is pretty much ready to go to try out a little test. So here's the new and improved, hopefully, electrolysis setup for testing these membranes. The electrodes, these graphite electrodes, just sit inside these little lids, which go right on top of the cell, and then there's a little port here for being able to put in the capillary for sampling gas with the mass spec. Just did that for convenience. Should be able to get a pretty good signal. I've got the mass spec recording in the back there on that screen. It's probably pretty hard to see. But the idea here is to see if we can show hydrogen generation is easy enough to show, but when using something like sodium chloride or really any other chloride salt, you generate chlorine gas on the anode, and that's it's pretty hard to basically pick up the chlorine on an RGA mass spec like I have, because it's so reactive that it basically reacts before it gets to the detector, effectively making it invisible. So I got a couple of other salts here. Got potassium carbonate, sodium acetate. The potassium carbonate should, all of these are going to generate hydrogen at the anode, hydrogen at the cathode, and then at the anode, this carbonate one should generate just oxygen from the water splitting, so we should see oxygen peak go up on the mass spec. And then this one might be kind of interesting. So sodium acetate hydrolysis, or not hydrolysis, electrolysis, produces CO2 and ethane at the anode, and that should be really interesting to look at the mass spec. So that's what we're going to do. We're going to try out this new testing setup with a couple of these different salts. Alright, so we will just go ahead and add the potassium carbonate. Just a bit to each side of the cell. Now we'll add some water. So here's the cell. I don't know if you can see the carbonate in there. It's white on white, so it's kind of tough to see that. Filling up one side. I'm going to try and get these relatively level to each other, so that way they see the same electrode area exposure. This isn't exactly super precise work, but this should be much better than the other tests that I did with the hot glued membrane in a little cup. Okay. So here's the anode. Here's the cathode. Okay. So right now I'm gonna have the mass spec looking at the anode side. Which should result in higher oxygen. Okay. Bit higher voltage. I think I might have let these dry out a little bit too much, unfortunately. The membrane, that is. So it's gonna have to sit for a bit. Okay, I've let this sit for a couple of hours with the liquid inside to rehydrate the membrane a little bit. I don't know if that's exactly the right term, but it seems like if the membrane totally dries out, it takes a while for the resistance to drop back off. So I'm going to turn it on. So now we're at about 75 milliamps. Let's see if we can kick that up a bit. Yeah, so it's taking 30 volts right now to drive 140 milliamps. But that should slowly be increasing. You can see it's increasing right now. And then I have it limited to max out at 1/5 of an amp. Once it reaches that, the voltage will start dropping off. And let's see if we see anything on the mass spec. So right now I am sampling the anode, so we should see an increase in oxygen concentration. So here's value right now is nitrogen. Here's all the peaks I'm keeping track of. This is nitrogen. We have a slow build of oxygen here. Yep. So oxygen does seem to be increasing right now. It's a good sign. Everything else is staying mostly constant. Oh yeah, oxygen is definitely going up, it looks like. So we started with this value of oxygen at this point in time. Now, if I move over, we are up a bit. I'm gonna let that run a little bit longer. Okay, and we're getting closer to that 1/5 of an amp limit. I'm going to remove the capillary inlet and see if our oxygen levels drop back off to normal atmospheric ratios. And actually we can watch it in real time. So now I've removed it and look at that. The oxygen is dropping off. You can see that right there. And then we can do the same thing with the other side, except this time it should be hydrogen. That starts increasing. And there it is. Huge response right away. Hydrogen tends to respond quickly. Look at that peak. It's just climbing right away. Ton of hydrogen. Looks like maybe a little bit of CO2 as well here. Peak 44. Sort of going up. Probably try and make save these graphs so I can actually point to them in the video. Be a little easier to show what I'm talking about. But yeah, that's a pretty good response there. We're about to reach, yep, there's that 1/5 of an amp, and now see the voltage is going to start dropping relatively quickly to maintain that 1/5 of an amp, and that should drop quite a bit over time. I'm going to take another look, see if I can see the oxygen increase in here. And there it is. So again, I have it in the anode cell. You can see pretty clearly the oxygen peak starting to increase here again. Not nearly as prominent as the hydrogen peak, But interestingly enough, the CO2 is really kicking up quite a bit. So that makes me wonder if the carbonate is then maybe making a carbonic acid or something in the cell, and at us it's reaching a solubility limit, and so because usually CO2 makes an equilibrium with carbonic acid in water solution, slightly acidifying the solution, and so if I have more and more of that carbonic acid, you're going to have more and more CO2 in equilibrium, and eventually you're going to hit solubility limits, and it will start driving out, exiting the water as CO2 gas, and so I think that's kind of what's happening here, because yeah, the CO2 peak is responding pretty strongly on the anode side. Okay, now let's try it with a different electrolyte. Instead of the potassium carbonate, we'll use the sodium acetate. Okay, so again, we'll add our electrolyte here. Dissolves in an interesting way. Smells a little bit of an acetic acid, vinegary kind of smell. It's interesting. I guess that's the acetate part. Okay, let's try this some more. See what we can make happen here. Oh yeah, that's way better. So it's taking a bit under 15 volts to get that 1/5 of an amp flowing now. I don't want to dump too much power into here. Don't want to create too much heat, but let's increase that just a bit to get a bit more gas production, to see if I can get a signal response. I really want to see that ethane, those ethane peaks. I think that would be really neat if we can do that. Yeah, it really smells like acetone, or not acetone, acetic acid. I'll have to look that up. Okay, I think I'm actually getting a response now from a potential peak that has to do with ethane. Ethane, the dominant peak that ethane has is at mass to charge ratio of 28, and that is the same as atmospheric nitrogen, N2, but it's got other peaks at like 30 and 27 and that kind of thing, and I am actually seeing a noticeable increase. It's slight, but it's there in the 27 peak. And if I scan here, so this is before I insert the probe, 5.4, E-9, and then we're jumping 6.5 on the 27 peak. So that's a good sign. I think that might actually be an ethane footprint. And the CO2 is still rising. The CO2 is jumping quite a bit to the point where the dominant nitrogen peak is starting to sag because it's basically the partial pressure in the cell headspace of the CO2 is starting to take over, and so it's having an effect on all the other partial pressures. And they're decreasing. So yeah, I'm gonna let this run for a bit and get a nice graph, and then we'll take a look at it on the computer. The cells are holding up nicely so far too. Somewhat surprising. Okay, so I'm gonna go ahead and stop this. I think that is good. I'm pretty much good on the mass spec data gathering side. And yeah, I cranked it up to 0.4 amps just to get more gas. It worked pretty well. I'm gonna remove these. Now, I was noticing some sloughing maybe of the electrode. Maybe not. But it seemed like the anode graphite rod side was sloughing more when I wipe it off. That kind of makes sense. Yeah, I don't know if can see, but it seems like the graphite is sloughing off more on the anode side, and I think it's because the anode side is a lot more of a chemically harsh environment than the cathode side, maybe. Alright, now let's check pHs, see if the membrane worked as it's supposed to. So on the anode side, we are expecting to see an acidic pH. Hopefully that's what we get. Well, it's not quite basic. Probably like 5.5 maybe. 5.5. Maybe a little bit lighter than that. Somewhere, I don't know, about 5. So slightly acidic on the anode side. And on the cathode side, we're expecting it to be basic. Oh yeah. Yeah, that definitely. It's definitely basic. I mean, that's essentially off the scale. So it's past 9 for sure. Let's see, I've got these other strips that go to 14. We can get an idea of maybe how basic it got. So the membrane is definitely working, because otherwise both cells would be the same pH, and clearly you have a delineation in pH here. Oh yeah, super basic. So probably, man, that sure looks like 14 to me. I don't know, maybe 13 to 14, somewhere in there. But it's really, this isn't supposed to be all that qualitative or quantitative. This is just supposed to be a qualitative look at whether or not the membrane is maintaining a selective ion differentiation, which is causing the pH difference. So this looks pretty good. I'm kind of tempted to leave this for a bit to see how the PETG behaves in slightly acidic and then the highly basic solution, see if it degrades or not. I'd say overall though that this concept works very well as a test bed. It's definitely worked much better than hot gluing. So I think I'm going to be using these to do experiments with the membranes and get a bit better at making these membranes, because my membranes still are very, very bad. Here, this looks pretty bad. You can see spots where there's beads that didn't get all the way crushed, and it's just uneven. Yeah, especially if you look at this side, it looks mostly even, aside from all the random beads that didn't get crushed. Then this side is pretty bad. You know, you've got parts of partial coverage, some parts that are not covered, so I gotta work on that for sure. Yeah, say this has been a success.